Today we're going to talk about applications in electrochemistry. Faraday's law says that the amount of substance that's being oxidized or reduced at each electrode during electrolysis is directly proportional to the amount of electricity that passes through the cell. So knowing that relationship can help you solve these problems. There are different kinds of equations, but personally I like to use dimensional analysis to solve them. If you know that 1 volt, for instance, is 1 joule per coulomb, 1 amp is 1 coulomb per second, and if you know Faraday's constant is 96,500 coulombs per mole of electrons, then the dimensional analysis problems really become pretty easy. For instance, question, what mass of cobalt metal is plated when a current of 15 amps is passed for 60 minutes through a solution containing cobalt-2 ions? First of all, knowing that 15 amps is 15 coulombs per second is going to help out in doing these dimensional analysis problems. Knowing that you're dealing with a cobalt-2 plus ion is also going to be important here in just a minute. So we know that we have this 60 minutes of time that current has passed through this system. So let's start with that. Always start with the simplest unit. So 60 minutes, and the fact that we have 60 seconds per minute, and we have a value up here in amps, but when we convert it to coulombs per second, we have 15 coulombs per second. It's going to fit in really nicely with our dimensional analysis problem. What else do we know about coulombs? We know Faraday's constant. We know that Faraday's constant says there's 96,500 coulombs per mole of electrons. And we just said that this was a cobalt-2 plus ion. Think about it. If you have a mole of cobalt, then for every mole of cobalt, you're going to produce 2 moles of electrons. So 1 mole of cobalt, got that on the wrong side. It's a beauty part of dimensional analysis. It doesn't take you long to figure out when you make a mistake. So like I said, if you've got 2 moles of electrons, then that's going to be equivalent to 1 mole of cobalt, since it's a 2 plus ion. 1 cobalt would give you 2 electrons, so 1 mole of cobalt would give you 2 moles of electrons. And finally, if you have your value in moles now, because so far everything is canceled except for moles of cobalt, we want grams of cobalt. Now it's simply molar mass, 58.93 grams of cobalt per mole. And that's going to give us a value of 16 grams of cobalt. So again, the dimensional analysis becomes relatively simple if you know how to convert those units into some of those base units. So look at the next one. It says, how long will it take to plate out 1 kilogram of aluminum from aluminum ions using a current of 100 amps? Well, first of all, let's do a little bit more specific than how long. Let's say we want to know this in hours. 1 kilogram, all of our molar masses are in grams, so let's just go ahead and convert that to 1,000 grams of aluminum. We're dealing with aluminum ions. That's going to be important here in a minute, knowing that aluminum isn't always true 3 plus, because if we have 1 mole of aluminum, remember we're going to produce 3 moles of 3 moles, of electrons. So, and we're using a current of 100 amps, and 100 amps, remember, amps is coulombs per second. So now we have information that will get us started on this problem. If we start with the simplest unit, we're going to be starting with the 1,000 grams of aluminum. Using our molar mass of aluminum, 26.98 grams per mole, we now have it in moles of aluminum. And we just established that if we have 1 mole of aluminum, we're going to produce what? Exactly, 3 moles of electrons. What do we know about moles of electrons? Well, we know Faraday's constant, that there are 96,500 coulombs per mole of electrons. And we just established up here that there were 100 coulombs per second. And since I established that I wanted this in hours, I'll just shorten this a little bit and say that there are 3,600 seconds in 1 hour. And once we solve for this, canceling out all of our units, we see that we have 29.8 hours. So again, dimensional analysis on these problems works really well. So let's go on and talk a little bit about spontaneity of cells. Remember our favorite conditions. Well, now we talked about them in terms of negative and positive, but sometimes AP talks about them in terms of greater than or less than 0, and we don't want our brains to glitch in and in. So remember, delta H less than 0 is a negative delta H, delta S greater than 0 or a positive delta S, K greater than 1, delta G less than 0, so again a negative delta G, and finally E cell greater than 0 or a positive E cell. So those are our favorable conditions. We talked the other day about the meaning of life equations, and that's our relationship between thermochemistry, equilibrium, and electrochemistry. And these 2 equations will give us relationships between those 2 systems. The Ganiffy equation here, delta G equals negative N times Faraday's constant times E cell. And then our negative Ratlink equation that we've talked about before, that delta G is a negative RT times the natural log of K. Notice that G down here is free energy. N is the number of moles of electrons transferred. So we need to think about that when we're looking at these equations. Faraday's constant, 96,500 coulombs per mole electrons. Cell potential is E0. R, since we're dealing with equations that contain G, which is free energy, we want that to be our joule R, 8.3145 joules per Kelvin mole. Temperature, as usual, has to be in kelvins, and of course K is the equilibrium constant. So let's look at an example problem. It says calculate the E cell and delta G at 25 degrees Celsius for the following reaction. In addition, determine the equilibrium constant for the reaction. First of all, E cell we could calculate easily by looking up cell potentials and doing half reactions. We actually did this one in the previous set of notes, this exact problem, and we came up in the previous set of notes that E cell for this particular reaction was positive 0.78 volts. Recall that this is 0.78 joules per coulomb. Look at our example at the beginning of this set of notes. So if we know E cell, when looking at our previous equations, if we're trying to go between E cell, delta G, and K, we know that we are dealing with our meaning of life equations because we're moving back and forth between these major areas of chemistry. So since we know E cell, the equation that works with E cell is that delta G is equal to negative N times Faraday's constant times E cell. Now, N is moles of electrons involved. Recall that when we balance this, we are going to end up with, in this case, adding 2 electrons, in this case giving up 2 electrons. So we have an exchange of 2 electrons. So -2 is going to be the value here. Faraday's constant is 96,500 coulombs per mole of electrons. And then we just established that E was 0.78 joules per coulomb. This gives us 540 and this is a negative value. And if we look at our units, moles of electrons cancel, coulombs cancel, and we're left with joules. So there's our value for delta G. So we've calculated delta G. So delta G is going to be negative 1.5 times 10 to the 5th joules. And now we look at our next problem. Actually, this is joules per mole, technically. When we look at the next part of the problem, then, once we have delta G, we can use delta G being equal to negative rat length. And we've got our negative 150,540 joules per mole. Don't want to use our rounded value here. Is equal to negative R, and R is 8.3145 joules per mole Kelvin. Temperature, it told us up at the top, was 298 kelvins. Times ln of K. And we find that ln of K, if we divide this out, is going to be 60.76. Take e to the x of both sides, or inverse natural log, however you like to refer to it. We get that K is equal to 2.4 times 10 to the 26th. So if we know any one of these values using our meaning of life equations, we can determine the other two. Okay, our final example deals with conditions that are not standard. So if we look at this situation, we see that if we are not in standard conditions, we're going to use something called the Nernst equation. The Nernst equation simply says, and we usually use this one, that E is equal to E cell, E0, minus, that's, in other words, standard E cell, minus 0.0592 over N times the log of Q. So we're using the reaction quotient again from equilibrium. If we look at this example, we can see very quickly that it's not in standard conditions, because it wants us to calculate this voltage. It actually gives us E cell for standard conditions over here, but notice what we've got right here. We've got values for the molarity of our two solutions, and they're not 1 molar. And as soon as they're not 1 molar, this is not in standard conditions. So that's why we have to use the Nernst equation to calculate E cell. Now, I probably should have gone in here and put down what these values, or excuse me, what state of matter these were in. Aluminum's a solid. Both manganese and aluminum ions are aqueous. And then we've got manganese is also a solid. So the first thing we need to do is to calculate Q. We know we've already got E cell. If we look at what's happening here with our reactions, notice we've got a 6 electron change here. We've got a positive 6 here. We've got a positive 6 over here. So what's happened is we've had 6 electrons changing hands. That's a transfer of 6 electrons, which is going to be involved when we do this equation as the value for N. So if E cell is 0.48 volts, let's again look at the only other value that we need to calculate, and that's Q. We know that Q is going to be products over reactants. Remind yourself that solids are not involved in the reaction quotient or equilibrium constants. So what we're going to end up with is our concentration of aluminum cubed, it's squared in this case. Our concentration of aluminum squared divided by our concentration of manganese ion, and that should be an ion there. Concentration of manganese cubed. And we've already established that aluminum is 1.5 molar. We're going to square that. Manganese is 0.5 molar, and we're going to cube that. And we end up with a Q value equal to 18. So now let's plug everything into our equation. We know that, as it says up here, E is equal to E0 minus 0.0592 over N times the log of Q. We established that E cell was 0.48 volts. We're going to subtract off the quantity 0.0592 over N. Remember, we already established that N was 6 times the log of 18. This comes out to 0.48 volts minus 0.0124. We end up with a voltage of 0.47 volts. So it did decrease the voltage by just a little.